Okay, so if you have a geometric random process, it can run on all kind of spaces. So just to simplify things, we will just run them on graphs, which is a relatively elementary object. So we have a graph G. So I don't know, with some vertices. And some edges. And the graph can be finite or infinite. And this is geometry. But we do some probability, so we can run a random process on the graphs. And there are many random processes, but two that come to mind, say, are random walk or percolation. So we can do random walk or percolation. We can do, these are two basic processes we can do on a graph. So we can, by random walk, okay, and let me say even simple random walk on the graph. So this is, the graph is finite or infinite. It will be always, it will have bounded, the degree will be always finite. So the degree of a vertex is the number of edges meeting at the vertex. And the simple random walk is just, we have Nicolas here. And you just, you pick the walker, just pick a neighbor uniformly among the neighbor, and he just jumps there. Say, we can do it continuous time or discrete time. But the walker just jump around. And so this is simple random walk. And another natural process is to damage the graph, or is just we can go to each edge independently, and for each edge E, we'll assign XE will be just a Bernoulli independent Bernoulli random variable, which will tell you if we keep the edge or if we delete the edge. So we take the graph, and we just, for each edge, we throw a coin, a biased coin, and we keep the edge with probability P and remove it with probability 1 minus P. Now, if we have infinite graphs, and the Z2 lattice is a nice infinite graph, so we can, I guess I'm talking about stuff that everyone here knows, but so forgive me. So if we do random walk here, this is infinite graph. We can do random walk here, and there are many questions one can ask about random walk and many properties. But to set things simple to make things simple for this talk, we can ask the question: will the random walk return to the starting point infinitely often, or will the random walk escape to infinity, or will just disappear in infinity? So this is the dichotomy between recurrence and transience. So this is, the random walk is returning infinitely often to the origin with probability 1, and this is escaping to infinity. Can one quickly, okay, so you can, I guess many people here know that on Z2, actually the random walk will return to the origin infinitely often, but if you will consider the binary tree, then it's an exercise to show that here the random walk will drift to infinity. The random walk will escape to infinity. Now, so we have here at least different behavior that appears in infinite graph between recurrence and transient, and both of these behavior behaviors exist. Now, for percolation, we have, I think this I don't have to define or explain. There is the notion defined in Van Sant talk of PC. So there is a critical P. Well, he was considering site percolation on vertices, but I just said that we remove edges, but it's the same theory. So for any graph, for any G, for any infinite graph G, you can ask whether there is a critical probability P, so that if you keep edges with probability smaller than PC, you don't have infinite connected component almost surely. And if you pick with probability bigger than PC, you do have an infinite connected component. And we saw, or even a sketch that site percolation on the triangular lattice, actually the critical probability was 1/2. Now, if you take G to be Z, what is the critical probability for infinite cluster? If your graph is the line, I'm going away. Sorry? 1. So PC Z is 1. So when PC, so this is a graph that is not interesting. There is no phase transition. So the most basic phenomena for percolation is that PC of G is smaller than 1. Then we know that if we change the order parameter P, we see different qualitative phenomena. So to finish up the introduction, what I want to do in the talk, the title of the talk was Expansions, Bottlenecks, and Random Processes. What I want to argue is that isoperimetric properties of the graph, the underlying graph, manifest themselves in the behavior of the random process on the graph. So just to set the language or the notion we will look at, what we will see is or what I will discuss is different behavior of the random walk, how the isoperimetric properties of the graph affect the different behavior of the random walk, or how do you see, using the underlying geometric properties of the graph, whether you do have non-trivial points, like you have a transition for some non-trivial P, or like in Z, you have a degenerate situation. So this was the introduction on probability. Now you know everything you need to know on probability. So now just a very basic isoperimetric notion. So the most rough isoperimetric notion is, let me use this picture. So this is our graph, and this is the set. Here we have a set of two edges. So if this is a set S, the boundary of S will consist on, this is the vertex boundary, will consist on all vertices that have a neighbor in S. So the boundary will be, in this case, will be this one, this one, this one, this one, and this one. And this one is not a boundary. Okay? And this will be the, if I have a set, this will be the boundary of the set. Okay, so if we have a graph G, we can define age G is the infimum over S finite non-empty of the size of the boundary over the size of the S. This is the linear isoperimetric constant, or the Chigger constant of the graph. So can you quickly give me an example of a graph where this constant is 0? Z. So age of ZD is 0. Proof?
Take balls.
Yes, take balls. Take arbitrary large balls. Now, can you give me quickly an example of a graph where it is not 0? 3. So age, exercise, age, binary, 3 is 1. And actually, so you might say, this is equivalent to exponential growth. I will not do it now, but exercise, no. You can, well, of course, you can have graphs that have uniform exponential growth around every vertex. It's very easy, but age is 0. So this age, positive age, tell you that every set has the number of edges going out is proportional to the size of the set. Very different from what we see in Euclidean spaces. Age equals 0, this is what is called amenable. In algebra, it's called amenable, and the positive age, this is like non-amenable. Now, let me refine the isoperimetric inequality and then go and say a little bit how they reflect in the study of random processes on the graphs. So here usually I'm confused, but okay. We want to define a notion of isoperimetric dimension, and I will, okay, so let me try to write a definition. So I stand for isoperimetric dimension of a graph G. This is a supremum of all the D's, so that boundary, so that there is C bigger than 0 for all S. This is finite non-empty. Boundary of S is bigger than the constant S to the D minus 1 over D. So I'm looking at the maximal exponent so that for every set, in the finite set in the graph, the boundary of the set is bigger than the size of the set taking to D minus 1 over D. This is a bit harder to get used to this notion than to the strong isoperimetric constant. But here, this is a non-trivial exercise. I deem ZD, we want to shoot at getting the right analog of RD, so this is D. So this is a more refined notion, and but on the other hand, it's you have examples of graphs that have infinite isoperimetric dimension. Cayley graph, nice graph, has infinite isoperimetric dimension, but still they will have 0 Chigger constant. If we will have time, I will just show very quickly example of such a graph. Okay, so there are other notions or related isoperimetric notions, but let's just start just with these two and see how they reflect in the study of probability. So Kesten, in his PhD, Kesten 59, Kesten 59, age G bigger than 0, return probabilities of simple random walk on G decays exponentially fast. This is just the inequality age g bigger than 0, or not. Well, there are precise inequality implies spectral gap, spectral radius smaller than 1 for, okay. So this is, I just wrote it informally. Kesten, so you saw the binary tree. The binary tree is an example of a graph when you have age binary tree equals 1. And if you think about a binary tree, it has this drift that push it outside, and to return after n step, it's harder and harder, and it's decaying. The probability to return after n step decays exponentially. So, actually, so if and only if return probability is of simple random walk decay exponentially fast. So you see a very clear relation between expansion and behavior of random processes. Now, I want to discuss a variant of Kesten's result. What happened if, say, we take the binary tree, we take the binary tree, and we percolate on it. We delete edges with small probability. So we know that if we keep edges with probability bigger than 1/2, we get a supercritical Galton-Watson tree. So we will have some, the percolation cluster will be a supercritical Galton-Watson tree. So if we percolate on the binary tree, percolate with p bigger than 1/2, we get a GW tree, supercritical family tree. So some edges will be removed, but still we get some exponential object. But of course, here, age of the GW tree, even if it's infinite, with probability 1 will be what? 0, at least in this case, if we percolate on the binary tree. Because we will have arbitrary long intervals very far away in the tree. We will have arbitrary long intervals that will drive age to 0. So we know now that return probability are not random walk on this Galton-Watson tree. The probability it's returning to the origin will not be exponentially small. But still, you want to say that there is some notion that this tree is still big. It still has exponential growth. So there is a variant, okay, of Kesten's result for such situations. So this is so age of the Galton-Watson tree there is 0 for this specific one. Of course, if you have the offspring is supported on more than 2 children, then it will be positive. But in this case, when we percolate on the binary tree for this binomial Galton-Watson tree is 0. But what if instead of taking the infimum over all finite set S, remember here I took the infimum over all finite set S and I got 0. what if I do the following variant? What if I do the following variant? I take H star G. I take the infimum of boundary of size of boundary over size of set for set S, which are finite, non-empty. S V belong to S for some specific V. I pick some V in the graph. I pick some V, some fixed vertex in the graph. S contain V and S connected. So instead of just taking infimum on all sets, instead of taking infimum on all set, I take just connected sets, infimum on connected sets that contained a fixed vertex. This is called anchored isoperimetric metric constant. So it's not trivial at all to see, but this is bigger than 0. And it's a little exercise to see that positivity is independent of the root. Just positivity is independent of the root. Now, a beautiful theorem of Balint-Virag H star G bigger than 0 imply simple random walk on G has positive speed. So this is a not so well known modification of Kesten's result to a non-uniform situation. But the proof, the classical result is by now very easily understood, and this is like from the late 90s, and it's very, very sophisticated and also very long. It's very beautiful result. Now, let me, okay, one more, before moving to percolation, one more thing is that isoperimetric dimension, due to the work of Varopoulos and his students, isoperimetric dimension control the decay of the return probability of the simple random walk, and in particular, so I don't know how to spell Varopoulos. Okay, Varopoulos, and this, so I deem G, say, bigger than 2, imply transients. Smaller than 2, recurrence. And in 2, it depends on the exact gauge. So it's not in 2, you need to go to a more refined isoperimetric profile to determine the type. So this was a very quick survey how isoperimetric properties of the underlying geometry can tell you something about behavior of random walk. Unfortunately, in the situation of percolation, we are still in a bad shape. So let me now move on to what isoperimetric properties tell us about percolation. No, I guess no. okay, take a binary tree and add to it a copy of z, just at the root. So you will get 0 star, but still random walk has positive speed. Right. Okay, so in percolation we are just more in the state of conjectures. So let's start with the rough conditions that ag is bigger than 0. So hz bigger than 0. So you have this like binary tree. You have this strong expansion. So this indeed implies PCG smaller than 1. This is with Oded Schramm, and but the main open problem, which is if you, I will not go to the explanation, which is more related to the Kesten dichotomy, is that we suspect that conjecture. Okay, let me write the conjecture first. Formally, Hg bigger than 0 imply that PC is smaller than something that I didn't define yet, PU. And let me say what is PU. Okay, let me write here what is I mean by PU. Not necessarily. In the binary tree, PU can be 1. But let me just write what is PU. So PU is infimum on P, so that there is a unique infinite cluster, almost surely. So by a result of Burton King, and actually before that, Chuck, Kesten and Eisenman prove uniqueness in ZD. In ZD, if you do percolation, once you are above PC, once you are supercritical, you have a unique infinite cluster. And by a result of Burton King, it knows that it's true for any amenable Cayley graph, or for any amenable vertex transitive graph. I will not go into that. So it's known that you have, once you have percolation, the supercritical percolation is unique, is some sort of perturbation of the lattice. It's dense in the lattice in ZD, but it goes beyond ZD by the Burton-King argument. Now, if you do percolation, what is on the binary tree? What is PU? Just to see that you got my definition. What is PU on the binary tree? Sorry? I said, but what? No. What is PU on the binary tree? 1. Okay, because take the binary tree and keep every edge with probability 3/4. So there will be a missing edge 1 someplace. And you know that on the two sides of it are full binary trees. So you will have, with probability 1, you will have here a cluster and here a cluster, but they will not be connected. So you know that for any P that you make, you percolate on the binary tree, there will be infinitely many infinite connected components. Now, it was observed first by Chuck and Jeffrey Grimmett that if you percolate on a tree times Z, you take a binary tree, and you put 1 above it, and you connect them. Oops. Just think on a stack of binary tree, and you connect this. So this is like t times z, it was observed that 20 years ago, it was observed that actually on this graph, for some p's, you have infinitely many clusters, but for some other p's, you have a unique infinite cluster. Later on, it was proved that for Cayley graph, you have uniqueness monotonicity, so that PU is well defined. There is a minimal point that above it for any P, you have a unique infinite cluster, and below it in ZD you have no percolation at all, but on some large graphs you have an interval where you have infinitely many infinite clusters. So the picture on large Cayley graph is no percolation for small order parameter for small p. Then you increase p, you get infinitely many infinite cluster. And for large p, possibly you have a unique infinite cluster. And a characterization of amenability, which is still open, but there are a lot of variants which are proofs, is that actually this is the case if G is a vertex transitive or Cayley graph. So we have a conjectural characterization of amenability, like Kesten has a random walk characterization of amenability for Cayley graph, and actually Pak and Smirnova which I think her husband will talk here sometime in this meeting, actually proved that for any Cayley graph, this is a side remark, for any Cayley graph there are generating set for which you have PC smaller than 1. So there is a percolation characterization, but still the conjecture is open. Now let's continue with percolation. So I said about how this manifests itself in percolation. Let me discuss the isoparametric dimension. So it was a Kesten conjecture proved by Varopoulos that every Cayley graph except Z1, Z2, and finite extension of them is transient. So for percolation, we believe that any infinite graph which is, you have it looks the same everywhere. You have automorphism mapping every vertex to every vertex. We believe that there is a PC smaller than 1. But this is still open. It is still open, unfortunately, sort of the analog of Varopoulos Kesten conjecture. It is called Varopoulos theorem. But since I don't want to define Cayley graphs here, I will just say that that Varopoulos theory, as I wrote it here, give you control on decay of return probability or the heat kernel in terms of the isoparametric dimension of the graph. So you would expect that if you have a graph with big isoparametric dimension, you would expect PC to be smaller than 1. So this is still open. So conjecture I dim G bigger than 1, but here it's okay, I can put bigger than any fixed number, we don't know. So if you do it for any fixed number, it will be nice. This implies that PC of G is smaller than 1, that you have a non-trivial, the graph is big enough to have non-trivial phase transition. So for ZD, of course, it's true bigger than 1 mean at least you are Z2. And we know that in Z2 we have a PC smaller than 1. And we accept it to, like in studying random decay of return probability of random walks, that people understood that what governs is the isoparametric profile, and you don't need the exact structure of ZD, but you have a more geometric condition. We expect this to be the case, but unfortunately, this is such a simple property, but there are so little techniques, so few techniques to show this, that we don't know how to do this transition. Now, this was sort of expansion. I was talking how, so far in the talk, so the title was expansion bottlenecks. I want to move the bottlenecks. So we discussed how expansion can tell us something. Now I want to say how maybe we can use something out of bottlenecks. So by bottlenecks, I mean that I have in the graph big part of the graph that are connected by a small boundary to the complement. So again, here I want to here I want to come close to some things that will be discussed or in this school. So if you have some graphs, and you want to prove that simple random walk is recurrent on the graph. So one way to do that is the Nash-Williams criterion. If you have G graph, and you have cut sets, you have sets, and there are sets Si, infinite sets I, disjoint, well, let's say nested, it's not necessarily, nested, disjoint, nested disjoint set separating, and I will explain. Separating V fixed vertex from infinity, so that sum 1 over the sizes of the set is infinite. I will explain. Then G is recurrent. This is the Nash-Williams criterion for recurrent. Nash-Williams. I think also 59. But it was well known. So what it tells you, if you have a graph, let me draw. So our graph is here. This is V. If I have a collection, say V is bounded degree for simplicity, but if we have a collection S1, S2 of set, what I mean set separating the V from infinity, every path of vertices from V to infinity is intersecting all of the Si, any Si, then a fixed S, then we say that S separate V from infinity. If we have a sequence of cuts like that, so they are very small in this sense, then this is, it's not equivalent. This is one side. If we have these bottlenecks, then the graph is recurrent. Now I want to ask here a question. So with Nicolas, we were trying a lot to work on the uniform infinite planar triangulation to show that the object you will meet later in the workshop to show that it is recurrent. But we cannot establish existence of such sets. But say I give you the following, which is not the uniform infinite planar triangulation. Assume we have a graph G. G, it doesn't have to be planar, but G satisfy the following: BR volume of any ball. Okay, BR is ball of radius R. So okay, I will write it the following way: for all R and U in G, B, U are the size of a ball. Any ball of radius R around any vertex, the graph is up to a constant, grows like R to the D for some D. So it has a uniform, this we call uniform polynomial, uniform polygrowth D, which is not the case where you have a random geometry. But let's assume we have a graph that has this property. And it has another property. It has another property. So this is one, and property star. For all R and U, there is S. S is containing B, U, R, and is contained in B, U, 10R. So that boundary of S is smaller than R. So we have this notion of bottleneck. At every scale, so I take U, any U in the graph, I take a ball of radius R, and I take a ball of radius 10R. I know that there is a set here that contains the ball that has a small boundary. So the graph, D can be very large. But this set has a boundary which is linear in R. Okay? So I don't have a counterexample that such a thing is not recurrent. So my question for you, I guess it will be easier for you to come up with a counterexample. But the question I want to ask, does uniform growth, so let's call this condition triangle, does this plus this imply recurrence? Now, let me tell you something. So if you think on ZD, ZD satisfies this property, but you don't have this property because the IDM is D. But let me tell you, any planar graph satisfies, any planar graph for which this hold satisfies this. Any planar graph, it doesn't have to be the uniform infinite planar triangulation. This is a side remark. Planar graphs have this, just because of planarity, if they have uniform growth or doubling property, for people who know what is doubling property, it immediately implies that stars hold. Now, the uniform infinite planar triangulation doesn't satisfy this, but it satisfies a asymptotic version of this. So this is an open question. My guess is maybe no, but it will be very useful for us to know if the answer come up yes. Now, okay, so now I will say one comment and then two fun questions. So And here is a conjecture. Conjecture star plus this imply, and I will say speed exponent of simple random walk is 1 over d conjecture. And I will tell you, assume you have a graph that balls grows like r to the 4. Balls grow like r to the 4. But unlike z4, at every scale it has a cut. So here you have a ball of volume r to the 4, but it's separated by a cut from infinity, which is of size r. So the random walk will have hard time to find this set. So we expect that after n steps, speed exponent of random walk mean that d0 xn, this is n-step random walk, is like n to the 1 over d. So the bottlenecks, I'm not sure whether they are enough to imply recurrence, but what I believe is that if you have huge growth, say like r to the 4, d equals 4, for example, but you have at every scale, you have a bottleneck, then we suspect that it takes the random walk have hard time to go to infinity. So unlike random walk on ZD, which is diffusive, we suspect that here it will have to slow down, and maybe even this is just so diffusivity is a conjecture, but maybe this is more ambitious to say that the exponent will be 1 over d. So in particular, on the uniform infinite planar triangulation, we expect that maybe by time n, the random walk is distance n to the 1/4. Okay. So, well, I can okay. I have one. Okay, maybe I end the first part of. I thought of maybe one more topic. I end the first. I end the main talk, and now I go to, since I was asked to give the late night, now I go to some completely independent fun. So now this is unrelated to the talk, just something for you to think at night. Okay, maybe if you have questions before I move to this, because this is, if you have any questions. Okay, so what I have here is, these are circles. These are congruent circles. And this is the hexagonal packing. So I try to draw it as good as I can. And this is the packing, the square, with packing with the circles with the square pattern, okay? So now I do the following, I play the following game. So I take this configuration, and this is in all of R2. This is in all of R2. Now I play the following game. Each disk, I take time epsilon, and each disk, the center of the disk, perform an independent time epsilon branch. So each disk is just perturb its position a little bit. Okay? Am I clear? So I move each disk. The center is doing a little epsilon time Brownian motion and move a little bit. So I perturb this picture. Okay, now my question, will the union of the square will contain an infinite cluster? Who vote for yes? Who vote for no? Who didn't understand the question? Okay, so I will repeat myself. I take this infinite configuration of disks. I just take the square lattice, and on each vertex I put a disk with a radius 1/2. So they are tangent, the disks. Now each disk I perturb it a little bit with a short run. The disk is doing a epsilon time Brownian motion, and all the disks do it independently. Now I'm asking whether the union of the disk will percolate. And now, before you answer, okay, the question is clear now? Now I ask the same for the hexagonal lattice. So I take the triangular lattice now, and I put disk of radius 1/2 on the center, on the vertices of the triangular lattice. This is the well-known hexagonal circle packing. Now I perturb a little bit with a small Brownian motion. I perturb a little bit the disk. Okay, so now let's do a vote. Who thinks that once you perturb here, the union of the disk will contain an infinite cluster? Okay, now the same question here. Who thinks when you perturb here? Okay, and now the answers, and then the question. So indeed, here, if you make the perturbation, no percolation. And here, if you perturb a little bit, there will be an infinite cluster. But, so here, we also know that if you take epsilon to be very large, there will be no percolation because it will converge to just continuous percolation with Poisson centers. And then here we need to rely on some, you need some Monte Carlos. There is actually the bounds, the rigorous bounds are not sufficient, but it is clear, or if we are physicists, just the true, not the proofs, then for large time, for short time, this will percolate, and for large time, this will not percolate. Here, this will just not percolate. Now, this is something I'm discussing now with Alex Stauffer, Brazilian. So what we don't know to show here is that we expect that there is a deterministic T0, that there is a critical time where suddenly it's not percolating anymore, because as time increases, it converges to continuous percolation, which doesn't percolate, and we can show that for small time it does percolate. So the question I want to tell you, to ask you, question, assume at T0, so if I run Brownian motion up to times T0 in this model, I tell you almost surely no percolation. T1, this is just a formulation of the existence of a deterministic model. T1, some fixed time, fixed, bigger than T0. Show almost surely no percolation at T1. Okay, thank you.